Hi, I'm Luke Booth. I'm an application engineer with SEL. At SEL, we designed what we're calling high-density coordination solutions. These solutions allow you to reduce the time and resources it takes to add a recloser to a circuit, as well as allow you to add as many reclosers as you want to. Here at SEL, we've heard from our utility partners that utilities are looking to increase the reliability of their distribution systems by adding reclosers. You may be one of those utilities, but we've heard you may be facing a couple of challenges. One is adding a recloser to a circuit that already has a lot of reclosers, or you don't have the time and resources to perform a recoordination study. What if you could reduce or eliminate recoordination studies, add as many reclosers to a circuit as you wanted to, and still achieve selectivity? That's exactly what the solution offers. I want to begin by describing the solution to you. I'll start with a simple circuit and then move towards more dense circuits. Take a look at this circuit with me. Here we've got a feeder protecting a typical distribution circuit, and we want to add a downstream device. It's imperative that we achieve selectivity. The device closest to the fault will operate for the fault. To do this, traditionally, we would create a curve that is coordinated with the upstream device by some coordination interval, so that when a fault occurs downstream of R1, R1 will operate and B1 will not. So we'll achieve selectivity using time. But consider a different approach with me. What if we copied the pickup, curve, and time dial in B1 and placed it into R1? Well, when the fault occurs now, both B1 and R1 are going to operate because they're using the same curve. But this is intentional. B1 is going to close back, and when it does, it provides healthy voltage to R1. R1's been waiting on that healthy voltage. When it sees it, it's going to enable a fast curve. That fast curve is now coordinated with the upstream curve. So what it's going to do is when it closes, if the fault is still present, only R1 is going to operate this time. So then R1 is continuing to go through its reclosing cycle on this fast curve until either the fault goes away, or if the fault's permanent, it's going to go to lockout. So we've achieved this selectivity, but we've also reduced the stress that's going to be on the power system because we're using a faster curve, which means less time for the fault current to be present. So without reviewing fuse sizes or redoing a coordination study or really much of any setting changes, we've achieved the selectivity that we've wanted. And we've done this using voltage, reclosing, and a fast curve. It's basically voltage-guided reclosing. Now, what if you wanted to add to this circuit another recloser in the future? You could easily do that by copying the curve, pickup, and time dial of B1 and R1 into R2. And you'll get the same results. And there's no need to wait. You can copy and paste. This is plug and go. Now, the other thing we've designed into this solution is that when the fast curve is needed, it's going to be supervised by second harmonic content. And this is a benefit so that when you're energizing the line, you're not going to operate for inrush current. Also, if you study this, you'll realize that we're going to prevent conductor slap miscoordination. Now, you may be a utility that has 2 or 3 reclosers already coordinated on a circuit, but you're getting more and more loads connected to your circuit. In this scenario, you want to increase the reliability by adding 4 more reclosers. So you're excited about this, you've been given the funding for it, and you go look to coordinate everything, and whoa, you realize you've got to coordinate 5 reclosers with an upstream breaker and a transformer damage curve. So you're going to think, I have to put some of these into sectionalizer mode. Well, this solution will allow you to keep all these reclosers in protection settings, protection mode. Protection is at every switch. Let me show you how we can do this. What we're going to do is we're going to copy the pickup, curve, and time dial of R1 and place it into R1A and R1B, effectively creating a group of reclosers using the same curve. Then we'll copy the curve, pickup, and time dial of R2, place it into R2A, and R3 into R3A, creating two more groups. So now group 1 is going to be coordinated with group 2 and group 3. So that when a fault occurs in any one of the groups, only that group is going to operate. So consider a fault downstream of R3A. In this scenario, only R3 and R3A are going to operate because group 3 is coordinated with group 1. So now R3 has healthy voltage, it's going to close back. It provides healthy voltage to the source side of R3A. R3A is going to enable its fast curve, it's going to close back, continuing to test that fault, and if it's permanent, go to lockout, still achieving the selectivity that we wanted. And notice we can easily add a device to any group using the same approach. And we haven't added any hardware to do this. This is a cost-effective solution. We've noticed, though, that a lot of customers who are investing in this number of reclosers are also wanting to perhaps invest in communications in the future. That would add some benefits. If you had peer-to-peer fiber communications for protection speed purposes, you could lower the time to trip down to 3 cycles. And you achieve greater selectivity by only tripping the device closest to the fault. We do this by a blocking scheme. In the blocking scheme, each device that detects a fault will send a block to its neighbor. You must receive 2 blocks to restrain unless you're an edge device. An edge device is the feeder or the most downstream device. If you only receive 1 block, you're going to trip after a short 3-cycle delay. So consider a fault downstream of R1B. Here will be the blocking signal sent in this scenario. B1 is going to restrain because it receives 1 block and it's an edge device. R1 receives 2 blocks and restrains. R1A receives 2 blocks and restrains. And R1B receives 1 block. It waits to receive any more blocks. It will not receive them. And it will trip after a 3-cycle delay. It would continue testing the line and eventually go to lockout if the fault was permanent. You can see that we're going to achieve selectivity here using peer-to-peer communications. And this blocking scheme is beautiful because it would apply to any topology. Now you may be asking, well, the blocking scheme is dependent on peer-to-peer communications. What if communications were to go out? If this happens, you can revert back to the no communication solution. If you started with the no communication solution, you would know that it's proven and tried and true. So don't wait to get communications to try this out. You can go ahead and start enhancing the reliability of your system using the no communication solutions, and then when fiber is available, add the communications solution. So I hope that you see that high density coordination, HDC, is simple, scalable, and applicable to any distribution system. Thanks for watching.